absolute pleasure to introduce Paulo Teixeira from the quite a mouthful.
Yeah, the last Lisbon Polytechnic. Okay, and Lisbon University.
Okay, I really look forward to telling you about this was planning to complain and a little more. Thank you very much.
Thanks for that. Right, thank you. It's a great pleasure to be back here in Aberystwyth, and yes, this is the official way we are supposed to write our affiliation. So basically, I'm at the School of Engineering of Lisbon Polytechnic Institute. That's where I teach, and I'm also a member of the Centre for Theoretical and Computational Physics at Lisbon University, which is where I do most of my research, where I carry out most of my research activity. However, the work I'm going to describe today is actually old, like 20 years old. No, this is something I did as a young postdoc back in the dark ages, if you can call it that. But still, well, it was suggested that I talk about it, and I went back to this fairly old work, and it looks like there hasn't been much development in this area. So, well, let's talk about it. I ask your forbearance because I may be a bit rusty on some of the more technical details, and being a physicist, I may not be quite up to scratch on the most recent and most sophisticated mathematics literature. So please bear with me, and if you know anyone who's done better, if you've done better yourselves, if you know references that I've missed, if you can spot obvious mistakes that I've made, then kindly let me know, and I'll try to fix whatever is wrong and fill in whatever gaps there may be here. So before I start in earnest, this was work, as I said, that I did as a young postdoc with the late Manuel Fortes, whom some of you will have known. Sadly, he's no longer with us, but this is basically his ideas as realized by me, and there was also a contribution by François Carner to some of this work. So here are all the relevant logos. And now we move on to the seminar proper. So let's go. This is about tiling the plane, or some parts of it. So some background first. We know the answer in 2D. We know what the list perimeter tiling of the plane is. How do we tile a plane with identical regions such that the total amount of perimeter is as small as it can be? And this had been conjectured many centuries ago by Kepler, if no one else before, and it was proved by Tom Hales fairly well, by mathematical and physical standards fairly recently, considering the amount of time that lapsed between the conjecture and the actual proof. Okay, so you tile the plane like this if you want to have this perimeter. Well, what next? We can ask ourselves, well, what if all regions are not identical, i.e. the monodisperse tiling, but what if there are two different regions of areas, say 1 and lambda? Essentially, we are taking the area of one of the regions as your unit of area, and lambda is the area ratio for the two regions. So what happens if we have two different regions, areas 1 and lambda? And also, what happens if you don't want to tile the whole plane, but only parts of it? Okay, so it's two possible directions you can get, and which we will follow. And, well, the answer to this problem will basically be a foam. Now, that's a monodispersed dry foam, and the answers to the bidispersed problems I've just described will also be dry foams. And dry foams, as we know, are governed by Plateau's rules, which must be satisfied, but do not uniquely determine a solution. So there will be many possible solutions to this problem, and we need to find out which one is optimal in the sense of having the least perimeter. Now, we are going to tile the whole plane, or we are going to tile, in most cases, we're going to tile something that's periodic, So when I talk about least perimeter, what we will be doing, as I'll go in more detail in a moment, is to work out what the perimeter is per repeating cell, per unit cell.
Can I ask what you mean by rotational? Just mean
Well, just the arcs meeting at 120 degrees angles, and the curvature satisfying the Laplace law. Adil?
Yeah, in time of it offers by this first tiling payment, since you're talking about these perimeter partitions, there's a much more defined problem there.
Much more, sorry?
If you're talking about these perimeter partitions, that's a much narrower problem than by this first tiling plane, right?
Yeah, well, yeah, the bidisperse tilings could not, well, need not be this perimeter. I'll be concentrating on tilings that minimize the perimeter. Actually, all those that I'll be describing here are tilings, some sort of tiling that minimizes the perimeter per unit cell. Tilings, yes, indeed, tilings will be a more general term, not necessarily an optimal one, in the sense of minimizing perimeter. And again, please bear with me, I'm just a physicist. Sometimes I'm a little imprecise when it comes to mathematical language. Right, so next. Right, so the problems we addressed. First, what is the list perimeter partition of the plane in the region of two different areas, not just one? Then, what if we don't tile the whole plane, but just some part of it? And in particular, well, if we're going to have regions of two different areas, do the regions of a given area want to mix with regions of a different area, or do they want to segregate? I.e., do they want to mix or do they want to sort? This isn't obvious.
you have the same number of each different area.
Number of each different area. Well, I'll come to that. I'll come to that in a moment, because of course there are infinitely many ways you can do this, and you have to restrict yourself at some point. I'll come to that. Okay. And then this is actually related to some results for completely different systems, such as we will see, the packing of hard disks on the plane, and also potentially soft colloids, although I didn't go, in the end I didn't go down this route towards soft colloids. And towards the end, one more system, which is a little different. It's not a tiling, it's not strictly, well, it's 2D chains, basically a one-dimensional object that lives in two-dimensional space. That is, you take two-dimensional regions and you arrange them into something that's periodic in one dimension only, what we call a chain of regions. Originally, we would use the language of bubbles and call it a bubble chain. It's basically some object that's made up of two-dimensional regions, but which is periodic in one dimension. And we'll see that at the end of the talk. So now for the general strategy. Okay, so we draw candidate structures. Eyeball Mark 1 method. How many can you think of and draw? Nothing systematic here. We just think very hard, or Manuel thought very hard about them. And how many can we think of? And hopefully we haven't missed that. Right, and then you work out what their perimeter per unit cell should be. And sometimes this can be done analytically, sometimes you have to do some numerics, some fairly simple numerics here. Of course, now this is what you mentioned. Now, of course, there are infinitely many ways of thinking of bidisperse tiling. So you have to restrict your attention somehow. And what we did was we considered only periodic structures with either one or two regions of area 1 and one or two regions of area lambda, such that there are always equal numbers of regions of area 1 or area lambda. Of course, you can extend this to as many different regions as you like, and you can change the proportions 2 to 1, 2 to 3, 2 to 4, 2 to 5, whatever you like. There's no end to it really. And if someday I manage to get my hands on a student in the nicest possible sense of the word, I may be able to persuade them to carry this work further, but so far I haven't been successful. So there you have it. Right. And we assume that all regions of a given area are identical. Right. So there's absolutely no guarantee that we haven't missed anything. These were all the structures we could think of at the time. If you know of any more, if you know of any clever way to generate them, I'd like to hear. And again, we offer no proofs whatsoever. Again, I'm just a physicist. I have no idea how to prove complicated things. These results should all be treated as conjectures. Good judgment. Okay, so starting with a list perimeter bidispersed tilings of the plane. So here are candidate tilings with one region of each area per unit cell. These are just chunks of tiling. They are not unit cells. You can tell there's more than one unit cell there. And the notation is, this is what we call the 6161, meaning there is one 6-sided cell and one 6-sided cell per, one 6-sided region and one 6-sided region per unit cell. In this case, all cells, all regions are 6-sided. And you will have noticed that these are very schematic drawing, because of course, in general, the region sides are not straight lines. But remember, this was drawn in the Dark Ages when drawing things was a lot harder than it is now. It would be a lot easier to do it now. And you also notice there are thick lines and there are thin lines, and the thick lines are between cells with the same number of sides. The thin lines are between cells with different numbers of sides. And regions with different numbers of sides. I get a little confused with this notation sometimes. I mean regions, but occasionally I will go wrong and refer to them as cells, and I may even occasionally refer to them as bubbles. Please bear with that. It's just well, I get a little confused sometimes. But I think you'll know what I mean in each case. Right, so that's the 6161, that's the 4181, so one quadrilateral and one octagon per unit cell. That's the 3191, one triangle and one monogon, I think that's what it's called per unit cell. And that's the 2110 so one, decagon maybe, and one lens-shaped thingy per unit cell. Right, and then, sorry.
You know that that's not exhaustive.
Well,
The previous slide.
yeah, and
That must be on.
again, you may be right. This, as I said, this were all we could think of at the time. If you know of more, please let me know.
Right.
Are you suggesting these are already minimized?
Oh no! I mean, these are generic shapes for each of them. I'm not saying these are the ones that. I'm not saying that these side lengths are the ones that minimize each of these tilings. They won't be, for starters, they won't be straight.
What about the angles?
The angles aren't quite right either, because all angles have to be 120, and there they clearly are not. As I said, this was the best I could draw them at the time. And no, these are not the relaxed shapes, as you would say now. Okay, so the angles are wrong, the edge, the side curvatures are wrong. These are just schematic. Now, these are the tilings with 2 regions of each area per unit cell. So that's the 5272. There is no 5171 as far as we can tell, and the others are just different, slightly more complicated versions of what I showed in the previous slide. So that's the 4282, that's the 6262, the 3292, and the 2210. So this means 2 quadrilaterals and 2 octagons per unit cell. That's 2 triangles and 2 nonagons per unit cell, etc. And again, these are schematic drawings. And now what you do is you work out what the perimeter per unit cell is for each of these as a function of lambda, and you plot it. And you just look which curve falls lowest. And there will be different curves falling lowest in each range of lambda. That's the area ratio that you consider. And the results are summarized in that table there. So you see that for small area ratios, which means if you have one of your regions very small and the other much larger, then the 3191 tiling wins, and that's, sorry, I'm going the wrong way, that's this one. And then the 4282 will win, that's this one. And then the 4181, that's this one. Then the 5272, which is this one. And finally the 6161, which is this one. So let's go back to the table. There you have it. So the sequence is 3191, 4282, 4181, 5272, and 6161, as you would expect, because this is in the limit of the 2 regions becoming identical, so it has to be the just regular honeycomb. Right, very good. But we have regions of 2 different areas. There's no guarantee they want to stay together. They could just as well sort into 2 individual monodisperse honeycombs. Do they? Well, let's see. So now, what this rather strange looking plot does is it compares the perimeter per unit cell of each of the winning tilings that I showed you before, just the winning ones. There's not much point in looking at the others that never win. And the perimeter per unit cell of 2 separate honeycombs. So this is the relative difference. Perimeter of each tiling minus perimeter of the 2 honeycombs divided by perimeter of the honeycombs. So this dashed line marks the 0 level. So it means that if the curve falls below 0, then the tiling wins. If it pokes above 0, then the 2 honeycombs win, in the sense that they have less perimeter than the tiling in question. The plot looks a bit funny because the horizontal axis is logarithmic. Okay, because there's a lot happening at small lambdas that we needed to capture, so that's why this plot looks maybe a bit funny. Anyway, we see that for small lambda we have the 3191 winning. Then there's a small interval there where 6 plus 6, that's 2 honeycombs, win. Then the 4282 wins. Then the 2 honeycombs win again. Then the 4181 wins. Then the 2 honeycombs win again. Then the 2 honeycombs win again. Then the 5272 wins there. And then the 2 honeycombs win again, and the limit of lambda going to 1. Of course, the 2 honeycombs become identical to the single monodisperse honeycomb. Right, so this is what happens if you allow your regions to demix, to use the language of physics and chemistry. So below the dashed line, you have your mixed arrangements, your mixed tilings. Above the dashed line, you have the sorted, regions sorted into two monodispersed honeycombs. Yeah.
Does this take into account there might be defects along the boundary between the two segregated regions?
No, because, well, I mean, we'll come to that in a moment when we do finite regions. Here we just considered, well, two universes, two 2D universes, one of them covered in a honeycomb of cells of regions of area 1, and another 2D universe all covered in regions of area lambda. So there's no interface here, because of course this is debatable whether this is the best strategy, but that's what we did at the time. These are, you just consider two copies of a 2D universe, one of them tiled with cells of area 1 and one with regions of area 1, and one of them tiled with regions of area lambda. So at the moment there is no interface here. We'll come to that in a moment. Okay, very good. Very good, very good. Now, it's interesting to compare the preceding result with something I found in the literature for packings of hard disks on a plane, which I think will be the Voronoi dual of this, I think, although I haven't checked that. Again, back in the dark ages, doing Voronoi tessellations was not that easy, and it's not something I ever learned to do. Maybe I should persuade a student to do that in case I ever find one who's willing. Anyway, this is just the results I've shown you. This is a summary of the results, including the possibility of sorting. So you see that you have these sorted ranges intervening between the different tilings, different mixed tilings that we saw before. And now here's the result for packings of hard disks. And you see that the sequence is almost the same, except there's something there that we don't consider. This is a random packing of disks, which apparently wins in some interval of area ratios. And also there's something different here. There's no sorted arrangement intervening between these two here. You look, it's different there. You go straight from 4181 to 5272, and then you have a sorted packing that intervenes somewhere halfway through the 5270 range. So there's some difference here, but the sequence 3191, 4181, 527. Oh, sorry, I've missed with no. There's something else. They also missed the 4282. 4282 is not here. So instead of a 4282, what they have is this random tiling, and for what 4181, 5272 sorted, then 5272 again, and sorted again. But well, it's not identical, of course, but there are similarities here that probably merit further attention at some point. In the end, I can show you pictures of some of those, if you're interested, which I took from this paper. This paper doesn't seem to have received much attention. I think it probably should. Right, now on for finite tilings, or tilings of finite domains of the plane. Right, if it's finite, what's its shape? Well, I think no one knows for sure. And this is the subject of much controversy, and it depends, I'm aware of that it depends on how many regions you have. You have to minimize all your total perimeter, including the perimeter of the outer boundary. You see you have air outside. Basically, if you think of this in terms of bubbles in a foam cluster. Right, so you have, you always have an outer boundary, and if you have sorted arrangements, you also have an inner boundary between the, in this case, the smaller regions inside and the, the smaller regions inside and the larger regions outside. So here you have an inner boundary as you do here and as you do there. And then you need to worry about what Simon mentioned, defects, but we'll come to that in a couple of minutes. Right, so again, the strategy was the same. How many sorted arrangements can you think of? Well, these are the mixed tilings of a finite circular domain. We just assumed they'll be circular. Of course, as I said, there's no guarantee that they will, but again, inspiration is drawn from foams, and if you have a large enough cluster of bubbles, then it sort of looks circular. So, okay, we just admit it is circular. More on that in a moment. Okay, so these are basically tilings of circular discs, mixed tilings of circular discs, or sorted tilings of circular discs. And these were all that we could think of. Either they split apart completely, or they managed to size segregate inside the disc. Either the small regions inside and the larger regions outside, or the other way around. The larger regions inside and the smaller regions outside, or one disc that's made up of large regions, one that's made up of small regions, and then they stick sideways. This domain sticks to that to give you something that looks a bit ugly, but it turns out that this is the one that always wins. Least perimeter of all the sorted tilings, this is the one that always wins. This isn't obvious. That's something we had to. That's something that we had to discover from calculation, because well, as I said, here there will be just the there's the perimeter. There's the perimeter per unit cell of your tiling inside plus the perimeter of your outer boundary, and then you also have the perimeter of your tiling inside, but that's just a honeycomb in either case, either a honeycomb of large hexagons or a honeycomb of small hexagons, plus the outer boundary, plus the energy of the boundary between the two honeycombs, the two monodisperse honeycombs. Right, so this is how we treated the outer boundary. Basically, this was originally formulated in the language of energies of bubble clusters. So you just average the energy of the orientationally average the energy of a monodisperse honeycomb, and we just took the same result for all of these. So all of these, the energy or equivalently the perimeter, because they just differ by a scale factor that gives you the unit of energy. So the perimeter of the outer boundaries is just approximated by the orientationally average perimeter of a honeycomb with the same area, with the same total area as each of these discs, and we did the same for all of these different timings of the disc. Again, it's an approximation. That was the best we could think of at the time. And again, now coming to the perimeter or equivalently energy of the inner interface. Yes, this is an interface between two mismatched honeycombs, two size mismatched honeycombs. And what you see here is a photo of an actual interface between two mismatched honeycombs in a bidisperse foam. So you see that smaller bubbles above and larger bubbles below. And what you see there is pairs of 5-7 defects. Now, this is known from material science, what the energy of such a wall of discriminations would be. And this is how it was approximated. Again, this was inspired by energy, but energy and perimeter, they just differ by a scale factor that gives you the energy scale. So what these approximations basically mean is that you assume some relationship between the perimeter of the boundary and your length scale and your bulk length scale. That's if you like. Right, what results? Now we need to compare the perimeters of each of those. In principle, we would need to compare the perimeters for each of those with the perimeters for each of these. But it turns out this one always wins, we checked that beforehand. So in the next slide, the perimeters for each of those will be compared with the perimeter for this. And now, as a function of lambda, the area ratio, and also as a function of how many regions we have in the domain. And we only consider domains with even numbers of regions. So when I say a domain containing n regions, what I mean in fact is 2n regions. It's n regions of area 1 and the n regions of area lambda. Right, so here's the result. It looks like the one I showed you before. In fact, the one I showed you before is the limit of this when you take n to infinity. So the curve lying below, so this curve line below is the one for a very, what I think is a very small number n of regions. And as you increase the number of regions, it moves up. So for small numbers of regions, you basically want to be mixed. But as you increase the number of regions you're considering, you start poking above 0. So you pick up those regions where your domains want to sort. For smallish domains, this is probably unrealistically small for the kind of approximations we're doing, but we just thought of including them for the good measure, sort of see how where it goes when we take a limit of relatively small number of regions. Okay, and as you increase the number of regions, as I said, you pick up these ranges where you have a size segregation, where you have sorting into the two monodisperse honeycombs. So these results are summarized in the following. Okay, what's this? This plots basically half the number of regions in each domain along the vertical axis and lambda, the area ratio, along the horizontal axis. So you see that if you're down here, that's few regions, then it's almost all mixed. But as you increase the number of regions, again, you start picking up these ranges where the two sorted honeycombs prevail. So, as I said, the sorted arrangement is always number 4, where you have a domain made up of just large bubbles and one made up of just small bubbles, and they stick to each other. Finally, you have this interesting sorting between mixed and sorted arrangements. Right, very good. Now, as I said, there hasn't been that much development along these lines, but we now know that things are not quite as simple, at least not. I think this is the way mathematicians express themselves when they want to say something is not too large or something is small. And here are some of assignments that some of you may be familiar with. that I took from a paper by Simon, and this isn't exactly the same problem because Simon, your outer boundary is fixed, isn't it? Yeah, your outer boundary is fixed. Okay, so it's irrelevant from the point of view of accounting for its length, because it's always the same for all arrangements. And but apart from that, I think it should have at least some relationship to the results I shared before. And what I think we see is that although this is not exactly the same problem, there are some common features here in that, look, if you have bubbles of regions that don't differ much in area, then they tend to be together. But if you have regions that do differ more in area, then, here regions of the same area tend to be together. So this would be a sorted arrangement in my language, and this would be a mixed arrangement. And again, just like in the results I presented you before, you have sorting if the two areas are more similar, and you have mixing if they're more different, which is the same kind of effect that we see in the results I presented to you before. And you see the same effect here. You see here, this would be, in my language, a sorted arrangement, and this would be a mixed one, or a more mixed one. Right, now enough of 2D, let's go on to 1D. Now, if you thought that was a large number of arrangements, now there are 22 of them. Okay, there's 22 ways to make 1D chains with regions of areas 1 and lambda, and no more than 2 of each per unit cell. And because they wouldn't all fit onto the same slide, I've split them between a number of slides. So that's what we call a 4-1 for 1. So that's one 4-sided region and one 4-sided region per unit cell. And this is 2 of them, also 4-sided per unit cell. And the same notation applies to others. And this slide shows regions that span the chain in the sense that they go from one side to the other. They go all the way across the chain, but there's nothing inside. There's no regions inside that don't contact the outer world, one side of the chain or the other. Okay, so just a second to allow you to soak in all the beauty of 1D chains, and then more. So next, now these don't go all the way across the chain, and again there are no inner regions. So here all regions are either contact the outer world on one side of the chain or the other, and there are no inner regions, sorry. Now there are inner regions like these, and regions that go all the way across the chain. And finally, no regions that go all the way across the chain and inner regions. Again, what I'm showing here is not unit cells, they're just chunks of chain, because it looks a little better, I think. Right, again, we needed to introduce one additional layer of notation because sometimes there can be more than one, as in this example, that there's more than one 2292 chain topology, so we needed to distinguish them somehow. So this letter subscript was added. Well, you do the same thing. You work out what the perimeter is per unit cell, and you plot it. But now you have to plot it not just as a function of lambda, the area ratio, but there's one additional variable here, because your cells can be either or squashed, in which case they would extend further across the chain, or they can be more squat if you pull on the chain. So we have something that we called not very felicitously the strain variable. It's basically a variable that parameterizes how squat or extended your chain is. And then for each lambda, for each area ratio, you plot the perimeter of the various topologies, again per unit cell, as a function of your as a function of your strain variable, of your variable that, as I said, parameterizes the shape of your cells. Well, you'll notice that some of these curves just terminate in odd places. This is because not all those different chains exist over the whole range of T and over the whole range of lambda. Okay, so you don't see all 22 of them here, you only see a few. That's those that exist for this particular value of lambda. And again, you work out which one has the least perimeter in each range of T for this particular lambda. And as you can tell by now, well, there's minimization with respect to two variables, so things are getting messy. Still, at the end of the day, you do it, and this is the result. This is your phase diagram in this two-dimensional space of lambda and T. And you can see that of all the 22 possible chains, there's only 9 of them that are ever optimal in some range of T and lambda, and they are shown here in this colorful plot, which almost certainly is wrong, because it really is messy. So I'm pretty sure I made a mistake there somewhere. Don't know where, otherwise I would have fixed it, but I mean, there must be some mistake. So there are 9 optimal chains. You see there are some re-entrants in some cases, and you have transitions between optimal chains that can be continuous or discontinuous. What do I mean by this? Well, sometimes curves cross, and then you have what I call a continuous transition between different minimizers, and sometimes they just end. And then you have a discontinuous transition in that you jump from one minimizer to the other. That's what I mean by continuous and discontinuous. Right, so there you go. So you see that the most popular arrangement here apparently is 4-2-4-2. Just to the simplest, which is one of the simplest ones you can think of actually. With 5-1-5-1 also doing well, and 2-2-7-2 also a popular choice. And some are never, well, this only 9 of them are ever optimal, which leaves out the other 13. If we didn't miss any, of course. Right, so this brings me to the end. So summary and conclusions. We have calculated candidate least perimeter, periodic tilings over plane-inted regions of area 1 and lambda, what's called equimolar, meaning that they're in 1-to-1 proportion, as many regions of one area as there are of the other, with at most 2 of them per unit cell. But if we allow them to be mixed, then there is alternation between mixed and sorted arrangements. And this has some relationship to the packings of hard disks on the plane. If we have tilings not of the whole plane, but basically of circular disks, then again we have alternation between mixed and sorted regions. And well, I say this is counterintuitive because I was thinking in terms of physics and chemistry, and usually in physics, when you have similar things, they tend to mix, and when you have different things that are very different, they tend to sort. So it is in this sense that I meant that the result is maybe a little counterintuitive, in that if we have similar things, regions of similar areas, they tend to size sort, whereas if they are very different areas, then they tend to mix. And it is in this sense that I mean that they might be a little counterintuitive. Okay, whether the above results would survive if we allow more complex unit cells, or if we allow aperiodic structures, well, we just don't know. And finally, we worked out the phase diagram for these periodic 2D chains, 1D periodic 2D chains of regions of, as far as we can tell, all possible topologies. Of course, all possible topologies that contain at most 2 regions of each area per unit cell, with equal numbers of regions of each area as a function of area ratio and basically region shape. And that was the colorful result that I just showed you. Right, so here we are. In case anyone's interested, here are the relevant references. And let me just thank our sponsors, and then I'll go back to this. Okay, so a word of thanks to our sponsors and to you for listening. And I'll stop here with this, which has nothing whatsoever to do with the subject of the talk. This is a photo of 2 threefold junctions in the liquid crystal foam, and it was taken by one of my colleagues, who's a liquid crystal scientist. And as I said, it has nothing whatsoever to do with the subject of this talk, but I'd just like to finish with something that's visually appealing. So there you go. Oops, start with that. Yes, go back here.
Great. Questions, please? Yeah.
Some of those little structures with little bubbles, look what I would call metastable. For example, if you've got a 2-sided lens in a perimeter minimizing system, surely that moves the vertex,
Right.
and forms a little triangle.
No, those never.
They never will.
No, they're not.
So, yeah, maybe you could save yourself some calculation, but that idea of moving to a vertex and doing T1,
Right.
does that allow you to enumerate all the possible clusters or unit cells?
Well, that's an interesting idea. I think that's an interesting idea for further developments. Like I said, if I ever get to do this for different proportions, like twice as many regions of area lambda as regions of area 1. That's I think that would be useful to try and work out as many of them. As far as the ones we consider just 1-to-1 proportion, there don't seem to be that many of them. I think we have all of them here. Maybe wrong. That's something I'll need to think a little about. But I think at the time we thought about this, we thought we had them all, and no one's complained in intervening years. So I suspect these are all of them in this one very particular case. But that would be useful if one ever gets to thinking of constructing tiles of different compositions rather than 1-to-1.
Yes.
That's the question. If you do realize this, there's a physical system which actually mixes all sorts, then as far as you usually have to worry about either additional forces that there's gravity, or about entropy, is something which favors usually the mixed states rather than the crystalline rather than the floating ones. Anybody want to comment on that? So especially when you say it's counterintuitive, what you're finding is that to do with the difference between the optimized system and the critical system.
First, well, this is QD, so I don't think gravity would play a role of it. Like so, I would say, but then we give it to display. And well, foam, as I said, the physical realization of this would be a foam which is essentially a zero temperature system. Yeah, but you're right, I should be a little more careful what I mean by counterintuitive when I try to make contact with physical, other physical systems that may exist at finite temperature.
I don't find it I mean, I suppose the picture of the 3D foam, that experimental one that you showed,
Yes.
that was vertical.
No, it's taken from above. So it's QD. No, there's no gravity there. So it's, yeah, you prepare them between perspective plates and then take a photo from above.
What then? But there must be some mechanism by which this segregation can dynamically occur. Or what is it?
I suppose you could shear it. You can shear it, and then that's one way of mimicking temperature. You shear it. You do various. You perpetrate a number of cruel actions on your phone, so as to get it to rearrange. You don't
know what happened to that particular.
I don't know what happens to this particular ones. Yeah, but that's something you can do. You can shear them.
Oh, thank you.
Can you show the diagram, lambda T diagram? In the two-dimensional problem, you said that lambda equal 1 means that you have same hexagons.
Right, lambda equals 1 means all regions are.
Yeah, and here, if you go up, if you go on the vertical line, lambda equal 1, you cross different stages, right? I was curious to know. I know that you show diagrams, but I don't remember honestly.
Okay, let's see. This is the 32. This is 3282B. So let's look for it. Can I write on this? Where's it? Here's attention. So let's just make a note of that.
So this is not really a one that is something that is two-dimensional but constrained, right?
It's something that's two-dimensional, but it's periodic along one dimension.
Yeah, okay.
Okay, so let's make a note. So first we have 3282B. 3282B. Then, well, starting say from here, then you have 5151. Then you have a bit of 4262. Then you go back to 5151. Then you go into 4242. And then you hit a bit of 2272. Okay, let's look at all this.
In a way, there will be some the topological chart will be.
Yeah, again, yeah, there will be certainly be topological changes here, but this is just equilibrium. The dynamics was not looked at. Okay, let's see how this goes. So can you see the 3282? Oh yes, here it is. This is the 3282B. Okay, and then 5151, which is not there. 5151, where is 5151? That's 5151. Okay, And then 4262, which is this one. And then 5151 again. And then 4242, which is that. And then 2272. Can you see 2272? No, it's not here.
Yeah.
Which is there?
Having bamboo 4242 and
Right.
case 5151 is like totally expected.
Okay.
The rest is up.
As I said, this was the best we did at the time.
No, I'm not saying it's wrong. It's surprising.
Right, yeah, it is, yeah, it is unexpectedly rich, let's call it that.
So 4262 is like an alternating staircase. But the two ends, 3282, 227.
Yes, and there's some pretty unexpected ones.
Let's just say.
Well, yeah, maybe.
Anybody else? I'm permitted to ask my own question and go on piece for a second. I'm very tantalized by the last bit you put up of liquid crystalline foam, something I've been meeting people about for a long time and asking if it's possible. So I just want to know what the state of the art is with that.
Well, it certainly is, because liquid crystals, many liquid crystals exhibit what's called a smectic phase.
Yeah.
The smectic phase is a soup, so you can make foams with it.
But you can definitely see some textures there that do
Yes.
very.
That would be a different seminar that I have not uploaded here, but I can show you. I'll be very happy to show you that.
Yeah.
Because I have these friends who work at the university across the river, and they do mostly liquid crystals and polymers.
Great.
But at some point they came up with this result, which is a beautiful liquid crystal foam, and you get these beautiful light and color effects because liquid crystals are optically active. But there's a lot more, because at the time when they showed me this, I thought, well, this sure looks like a foam, and it courses like a foam, and how much like a foam is it? So we looked at various things that you look at, various quantities that you look at when you think of foams, like number of sides of bubbles, and then how they course them, and do they do T1s and T2s, and they do a lot. And I'll be very happy to show you that. We looked at the statics, and we even looked at this, the liquid crystal foam and the shear.
Great, I'd love to find out more. Okay, let's thank Paulo once again. Thank you.